welcome to attend my session. And my topic is about data plane acceleration, usage, and programming in cloud-native NFV infrastructure on ARM, which talks about mainly about data plane acceleration work in our cloud-native software. This is my agenda. And firstly, I will give a brief introduction. And secondly, I will talk about the data plane development kit and all its architecture and core ideas and core concepts. And the third one is the data plane acceleration programming in high-performance user space network stack. And then I will talk about the data plane acceleration usage model in the FIDO VPP and OVS, which is two well-known virtual switching software. And then I will talk about the para-virtualized DPDK accessing mechanism, mainly about the I/O and the host mechanism and its usage in high-performance virtual switches. And then I will give a brief introduction about the data plane acceleration model, usage model in the host Kubernetes container networking solution with Contiv VPP, which is a famous container networking solution provided by Cisco. And the last one will be the performance evaluation with our various data plane acceleration use cases, which may include all the above scenarios with a brief performance evaluation for all the scenarios. Firstly, we would like to say something about what is data plane acceleration and what is cloud-native NFV infrastructure. Our aim for this topic is to give a point of view about the usage and programming model of the data plane acceleration techniques used in the typical software, which is used to build the cloud-native NFV network virtualization infrastructure. And what is cloud-native? Cloud-native is an approach to build around applications, exploit the advantages of a cloud computing delivery model. It's a well-known cloud-native infrastructure software is Kubernetes currently, which is provided by CNCF. And the data plane is in contrast to control plane. The data plane is to access the network packets and then to do some processing to the networking packets, such as forwarding and such as receiving, transmitting, or things like that. This layer is our core ideas to be optimized to achieve good performance, which is very important for the NFV infrastructure. The data plane acceleration is to improve packet forwarding performance. A lot of special non-traditional packet processing mechanisms would be introduced, such as user space-based power mode driver, and instead of interrupt-based driver, lockless ring, and to store packets, and during service calls to enable a dynamic way of performing work on CPU logical cores. And currently, the data plane acceleration development kit, DPDK, is a typical open source software to do that. And so we should give a brief introduction about the DPDK architecture and our core ideas here. And this is the DPDK architecture. The most important compartment of DPDK is as a power mode driver, which we will support all the typical on-the-shelf hardware such as I40E and IXGBE and the third-party NICs such as the NICs from Analogs, from malware, and all things like that. Besides the PMD driver, the users, the DPDK users mostly contact with its core libraries, such as the EL, the environment abstraction layer, to do the environment procession, and all the other libraries such as ring, timer, and memory pool, and all things like that. And from the right part of this graph, this is give us the DPDK drivers constructor, how to construct the DPDK library. The DPDK core ideas here is to use Power mode driver and to use user space driver, and to bypass the kernel procession. And to improve the performance, a lot of techniques have been used, such as use queue pages to know memory access cost, and use CPU core affinity to bind to a certain CPU to do all the run to completion model, and do batch packet procession, and DPDK also uses the CPU feature identification, which is vector instructions, atomic instructions to avoid lock, and software tuning for thresh code for PC access and avoid cache miss, branch mispredicts. And it will utilize all the hardware features such as the checksum offload, TSO offload, and all things like that. It will grab cores and place a single piece thread on each core. So I will illustrate all the running model of DPDK in the later slides. And each core will become a run to completion thread. And it supports not only the physical devices, but also the virtual devices, which is Virtio Vhost model. So I give a list of some typical features DPDK uses. Firstly, it uses polling methods instead of interrupts. Secondly, it uses user mode driver instead of kernel mode driver. And the pthread affinity, and the queue page, and the lock list intercore communication, and high throughput bug mode, all things like that. There are a lot of open source projects using DPDK. I had to give it a lot of software used here, use the DPDK here. So such as the SPDK, as you know, for storage, FStack as an open source software, user space stack, and such as Federal VPP, OVS-DPDK, Open vSwitch, and all things like that. So firstly, I will talk about our first many introduced software, which is user space network stack. Currently, this graph gives out the typical DPDK program model, which is intrinsic DPDK, native DPDK programming model. And for DPDK, there is a lot of CPU cores used, and which the user can indicate and configure which CPU cores can be used. And from this model, there is a master logic core, which is for the management and also do the data processing. For all the slave cores, from its initial state, it will do a simple loop to wait for the command from the master. After the initialization, the user triggers all the work, which the master core will trigger the slave cores to send a start message. So all the slave cores can do the slave thread procession in the main loop. So you can see all the business logic from this graph, from the bottom graph. In this page, I give out a simple DPDK programming model programming example here. Initially, we will initiate the EL layer, and it will process all do the initialization things for all the underlay DPDK procession, such as the memory pool, the initialization, such as L core initialization, all things like that. And then we will initialize and allocate the pod resources as pod rings, pod RX rings and TX rings, which is for the receive and transmit. And then we will do the core logical of this procession. And for each core, we will trigger all the each core to do the main loop, L core main here. Each loop in the loop will do all the receiving and transmitting things in this loop. So this is a typical DPDK procession in a DPDK programming model in a typical use cases. For the network high-performance user space network stack, and it's in this page, it gives out the F-stack. F-stack is a user space network TCP/IP stack based on FreeBSD, and it is provided by the Tencent, and it's widely used. I see that from the GitHub, it has more than 2,000 stars, and which is very, I think it's a very well-known and well-used user space TCP/IP stack for which support DPDK with high-performance user space network stack. And from this picture, you can see that it completely follows a DPDK programming model. And for each core, it will do the user space procession. You can see that besides the read and process packets from dispatch string and read and process packets from the Ethernet device, it will do the packet input and packet input to the protocol stack by the typical IF input, which is a typical FreeBSD network packet input. So this is for the combination between the user space network stack and the DPDK. And this page gives out a legacy IPv3 and IPv3 on F stack. And from the left part, the users can block all the procession or the block to wait for some special tag to initiate the approve test. But for the IPv3 on F stack, and you cannot block. You can block anything because all the processing are in a single loop. So all the things need to be changed to a long block model here, for all the signal processing, so all this message processing mechanism. So yeah, besides the user F stack, the user space network stack, all the other network cloud native infrastructure networking components are the vector packet procession VPP, which is provided by FIDO, and OpenVSwitch, which is very widely used today. For the VIDO BPP, and we know that it is for the vector packet procession to improve the performance for the packet procession, and fully featured with its network stack, we use all the network stack and all the packet processing are dispatched on the different nodes, and all the packet processing forms a complete node graph, which is shown in the right part of this page. And for DPDK is used for the fast I/O of VPP, and VPP now completely relies on the DPDK to do the network I/O, and so all the packet processing would be received and transmitted via the DPDK interfaces with the DPDK input node. And the DPDK works as the main network I/O accession mechanism technology for physical network devices in VPP. And in this page, I give out a typical code for our VPP accesses and utilizes the DPDK's API to do the network receiving and transmitting. And for example, the VPP uses RETH RX burst function call to do the packet receiving. And here we would like to say that there are two transmission and two conversions between the VPP's packet buffer, which is known as vleave buffer, and but the DPDK uses another structure, another buffer structure, which is named M buffer. So it provided two macros to do the conversion between the two types of buffers, packet buffers. And VPP uses the DPDK RTE library to do the transmit and receiving packets, but not the DPDK multi-thread running model. And actually, VPP uses on big loop for its packet procession, which is a little different, which is much different from the original DPDK programming model, which is all things processing in a big loop. The second well-known virtual switching software is the OpenV switch. OpenV switch also has supported from 2.5 to support the DPDK interfaces. Originally, it only supports the data path from the kernel interfaces. And after 2.5, and it supports the network device of DPDK. And actually, there are three kinds of DPDK interfaces in this DPDK. Three different DPDK classes. The first one is the DPDK Vhost-user, DPDK Vhost-user procession, which is for the virtual para-virtualized interfaces between the virtual machine and the OVS. The second one is the physical ports and the physical port and the physical DPDK, which is used for the actual packet processing and receiving and transmitting from the physical NICs to the physical NICs. And the third one is the DPDK DPDK IVSH-MEM. This one is for the DPDK ring class. DPDK ring class is for a certain kind of DPDK, a certain kind of virtual interfaces besides the what IOV host, but it is not used. It is not used now, but it is still kept here. So from this graph, you can see that from the right part of this graph, you can see that the native OVS uses a kernel space data module to do the packet processing. And it combined with the DPDK accession model. So it will we get an OVS-DPDK model from here, which combined the OVS user space forwarding engine and the underlay DPDK packet procession, DPDK packet receiving mechanism. So the packets can bypass the kernel procession, kernel interfaces, and utilized by the OpenV switch. From this page, I give out a data plane acceleration programming in OpenV switch. Typically, the left part is the vSwitch-D, which is for all the packet procession for the user space packet procession for the packet matching and packet matching and forwarding in the user space, which will bypass the data path kernel module for native OVS. And For the right part, this code is for the DPDK vhost class, and I give out the typical APIs used by the OVS-DPDK, which is used to and receive receive the packets from the vhost interfaces, and the transmit API calls to transmit all the packets, which for the vhost class. Actually, you can see that there are 4 DPDK classes, the native DPDK classes, and the DPDK ring classes, and the DPDK vhost class, and the vhost client classes. And for DPDK vhost classes, and there are 2 modes here, because typically we can use the OVS as the server and the user's virtual machine as the client, but we use it in another way, and the OVS can be a vhost client, and the virtual machine can be the server. And actually, the client can be the QEMU, So I would give a further introduction about the para-virtualized data path acceleration mechanism. We host the Virtio, and it's used in high-performance virtual switches. Typically, OVS, I will say more about it. Actually, Virtio is a standardized interface for virtual machines to access simplified virtual devices, such as block devices and network adapters. It's an interface between the host and the guest. And Virtio requires only why we use Virtio device. Virtio devices requires only the bare minimum setup and configuration and send and receive date, while the host machine handles the majority of the setup and the maintenance of the actual physical hardware. And the left part of this graph, and we give out a typical OVS-DPDK with vhost-user model. And for the virtual machine, it accesses the vhost-user with its Virtio interfaces by the QEMU KVM. And from the bottom side, we can use network DPDK to access the NIC, access the physical NIC. And the right part gives out the typical structure of the Virtio DPDK based. And for the yellow line, it gives out the data path. For the blue line, it gives out the control path. And all the things is the same as the left part, but it's in more detail, such as the memory address translation by our MMU, and the data path access is from the bottom NIC, from the physical NIC to the virtual machine in the user space. And the vhost-user protocol is composed of the control path and the data path. For the control path, and there is passed via the Unix socket, which the main information exchanged by the control path is for exchanging the memory mapping for direct memory access, and kicking the other side of if data is arrived, if data is placed on the Virtio queue. For the data path, it is implemented via direct memory accesses. And the Virtio net driver within the guest or lock is part of the instance memory for the Virtio queue. And the QEMU shares this memory access with OVS-DPDK via the control channel. So we have 2 run models for the OVS-DPDK for vhost-user. One is the vhost-user client, and another is normal vhost-user. So previously I said about the VPP utilizes the DPDK to do the packet processing and packet receiving. So you would like to see a typical cloud-native infrastructure which utilizes VPP, which named as Contil VP, which is also provided by Cisco. And in this model, the DPDK interfaces are used as the main VPP interfaces for the typical container network interfaces. And actually, the DPDK interfaces is for the collecting the ports between hosts, and actually for inter-host communication. And here we want to see, this is all about the Kubernetes component, which is for the management and by the Kubernetes. In this graph, the DPDK interfaces is for the data interface between the physical network. In this model, we can see that the two hosts, the two nodes, node 1 and node 2, communicate with each other with the DPDK interfaces. Actually, from the physical interface by the DPDK, we use the overlay communication model to communicate all the nodes. If we want to access one port from another host, it will has a static route and we will find a static route from our VPP VIF route table. And from this route table, we can find that for the DPDK interface to communicate all the things and do the VX line encapsulation to send the packets to the target node. So we have done some performance evaluation to evaluate the various data plan accelerated cloud native applications and software and use scenarios. Firstly, it's for the DPDK itself. We want to do the data plan acceleration, so we should firstly compare the performance of the kernel transmitting and the performance of the DPDK transmitting. Actually, in layer 3 forward example, the kernel DPDK performance of L is much higher than the in the native kernel stack. Actually, for the single core cases, the performance gain is much more than 10 times, and for the 2 cores, it also gains about 6 times performance improvement. And for the performance evaluation of data plan acceleration in Open vSwitch, that we can see that for 1 kilo flows, 1,000 flows, for 1,000 flows, the native for the physical to physical packet switching, and the performance gain is much higher, and which is and for native OVS it's only 246 kilobit and for packets per second. But for the DPDK OVS-DPDK, and there is again this 7.3 million packets per second. And if we have more flows, such as 1,000 flows, and we get more from the DPDK acceleration. The second one is for the third one is for the performance tuning and evaluation in the user space network stack, which is I previously said it's about the F stack. From the F stack cases, you can see that it's Nginx test for by the WRK. Not only from the bandwidth bandwidth, but also the RPS request per second. We gain a lot from the user space network stack. If we use kernel-based, when we use more cores, we get more performance improvement, because you can see that from 1 to 4 cores, 8 cores, the performance improvement is much higher, either from the bandwidth or the request per second we have used, which is for Nginx test. It's a typical web-based web support software, HTTP server software widely used today. The fourth one, I think, is OVS-DPDK multi-core scaling up performance. And multi-core. And we can see that for the, we can gain a lot from the multi-core uses. And when we have 1,000 flows, and the performance improvement may be 5. When we have 4 cores compared with 1 cores. And when we have 4 cores, when 4,000 cores, the performance improvement is also very explicit. And this is about the performance evaluation with the physical to virtual machines and back to the physical NIC. And this test with the Virtio. And as during the Virtio, we gain about 10% of the physical interfaces. And we have to reduce the transmit rate from the tester to the about 10%, and from 10% to 11%. And the L2 throughput by this cases can only catch up with 10% of the NIC of the 9th bit of the 40 gigabit NIC. And the last cases we evaluated here, the last performance evaluation is about our with Contiv VVP for the container networking. It's typical use cases. For the above one is Fnano. Fnano is an overlay solution for the in-host communication. We can see that the performance gains is much more than 10 times for the pin native. For the pin latency. We again with 1,000 times, which the upper graph is for the second level, and for Contiv VPP, it's a latency. The port-to-port communication latency is reduced to millisecond level. So this is all my session in my content in this session today, and the reference is given here. And I want to say special thanks to ARM CEOSS networking Shanghai team, which we had done a lot of performance improvement and performance investigation in all the software, open source software for the data plan acceleration. I want to thanks to all their work here. So it's all for my topic. And do you have any question? Okay. Thank you all for your time.